Alrighty. Going live. Going live. Shut up. The 403 to the HAZ, Mr. Nelson here, doing a video live in front of a studio audience who are gonna be quiet while I'm doing this. Thank you. We are into our new unit, Radical Function Transformations. Kinda like our old unit of just function transformations. So let's recall that function transformations looked like this. We had 4 letters that do various transformations for us. We got B, we got A, we got that H, and we got that K. Okay, and if this looks like alien speak to you, it just means that you need to go check out my function transformation videos. But let's recall, so if you did watch those videos, we would know that A and K, they transform my y coordinates, and B and H transform my x coordinates. My class is being really quiet right now because they are scared of me, as they should be. And we're kind of just finished everything, so I have some time to kill right now, so they told me they would just love to see how it's made. And I was like, guys, you see it every day. But they're like, no, we want to see the real deal. I'm like, okay, I'll show you the real deal. So here we are. Here we are. Shot.
This is very crazy.
This is weird. We're getting weird together. Okay, kind of like you're a little scared, but it's like exhilarating, and you're like, okay, cool. That's where we're at. Okay. So in our function transformations, A was our vertical stretch, right? So we multiply our y coordinates by A, by the absolute value of A. If A is negative, we get a reflection in the x-axis. Okay, so we reflect in the x-axis, and then it follows that. So if the absolute value of A, if just the value of A is a number bigger than 1, we stretch. And then if A is a fraction, it's between 0 and 1, we're going to get a compression. It's going to shrink. And all we have to do is multiply our y coordinates by our value of A to get those. B is A's evil twin. It does horizontal stretching, but it stretches by a factor of 1 divided by the absolute value of B. Okay? Or 1 over B. Actually, this should just be 1. We stretch by A, and if we just do 1 over B, then if A is negative, and we multiply by, say, a -2, that's going to give us both our reflection and our stretch. So we don't have to actually use the absolute value, but we need to know that that's the stretch factor. So if B is negative, it's going to be a reflection in the y-axis. Straight up, I have tried to make this exact video like 4 times, and every time I finished making the video, about 20 minutes of me just talking, just to find out that it cut me off about after a minute. So that's why I'm doing it right now, is because I have a real vendetta. The absolute value of B, if B is a number bigger than 1, we're going to get the opposite effect. We're going to compress. Because if B was, 3, if B showed up as 3, well, we'd have to multiply by 1 divided by 3. And that's going to cause a shrinking. And then if B is a fraction, a number between 0 and 1, 1 divided by a fraction is going to be a number bigger than 1, so we're going to get a stretch. So B is kind of the inverse of A. It behaves in an inverse way, just the same way that H and K are quite simple. K is our vertical shift, so we're just moving it vertically. And whatever it is, if K is positive, it's going to be up. If K is negative, it's going to be down. And then H is our horizontal shift, and like b, it likes to behave oddly. So it's going to be the opposite of whatever sign. So if I have a negative h here, it means I'm actually moving towards the positive x's. If it's a positive h here, it's going to be to the negative. So that's a quick little recap of our function transformations. So now let's take a look at how it applies to radicals. Now, our baseline function for radicals is y is equal to the square root of x. And if I was to graph that, it would look like this. It's kind of diminishing returns. And we can notice that I don't have any negative values of x here. My graph does not exist for negative x. Why is that? Well, it's because I cannot take the square root of a negative number. Okay? Square root of a negative number is imaginary. I is equal to the square root of negative 1. Anything bigger than the square root or smaller than the square root of negative 1, any numbers that are negative in a square root mean that it's impossible. We cannot take the square root of a negative number. And we actually have a name for the square root of negative 1, and it's I. And the only way to make I a real number that we can use in the real world, not in the imaginary world of computers, whatnot, is to square it. So if I square I, well, if I square that, I'm just going to get negative 1. This is not something we need to know, but we just need to know that we cannot have the square root of a negative number. And that's why, as soon as x becomes negative, this function quits working. So what if I were to have a function that looked like y is equal to the square root of x plus 2? Well, in this case, my function would end up looking like this, where this is negative 2, and it would exist into some negative values of x, because if x is negative 1 or negative 2, dealing with integers, well, that would give me the square root of 1. We're cool with that. And then if we use negative 2, we would get the square root of 0, which is still 0. It exists. But as soon as we get into numbers that are more negative than negative 2, like negative 3, we become imaginary, and we don't exist. And this, we can see, this is just a horizontal shift, negative 2. So that's actually an h. So that's just, we need to know that we cannot have negative square roots. So radical transformations, when we're dealing with radical functions, recalling that our original function.
Hey, students and teachers, today's go hockey is Marshall versus Bolt.
Oh, nice.
Message at the office for Savaya Basil. Message at the office for Candace Nickel.
So it's going to be A, 5. Bye, my little babies.
See you, loser.
Oh, love it. Can you feel the love? Okay. Bx minus.
You got the big game. I did.
I cried
Our
myself.
people to the office.
Sweet. Okay. I'm making a video right now. I'll come talk to you in a second, okay, Mackenzie? I just want to finish this. So this is what my function transformations look like for my radical function. My a, my b, my h, and my k all behave the exact same way as for other function transformations. So what I need to do when I'm working with these is create a table of values for my original function. And I am going to use that table as a reference. So my original function is this. I, being the incredibly smart, intelligent, good-looking person I am, recognize that the square root of any numbers that are not perfect squares is just going to be ugly. So I'm actually going to use perfect squares for x, because that will work well for me. So the square root of 1 is 1. Square root of 4 is 2, 3, 4, 5. This is what my function table of values looks like for these specific, for this domain that I've chosen. So let's say that I had a function transformation. I gave you an equation that said y is equal to
Happy birthday, Miss Nickel. Have an awesome day.
Happy birthday, Miss Nickel. 2 square root of negative x minus 1 plus 2. Say that was my function. This is my transformation. Well, the first thing I need to do is just identify what all my letters are here, what the value is. And I can see that the number outside my radical is 2. So A is 2. K is positive 2. B is negative, there's an invisible 1 there. B is negative 1. Negative 1. And H is negative 1, so H is actually a positive 1. We're moving in the positive direction. Remember, it behaves opposite. Okay? So now, knowing that A and K transform my y coordinates, and also remembering that I always apply my stretches, my A and my B first, and then I add or subtract H and K. So for my y coordinates, I'm going to make my new table of values, x prime, y prime, to represent the transformation. Okay, I'm going to multiply my y coordinates by 2 and then add 2. Easy enough. 2 times 1 is 2, 4, 6, 8, 10, 12. There we go. There's my new y's. Really easy. I just multiplied them all by 2 and added 2. Now I can do my x coordinates. And remember, I have to take 1 over b. 1 divided by negative 1 is negative 1. So I'm going to multiply all my x coordinates by negative 1, and then I'm going to add my h. So negative 1 plus 1 is 0. Negative 4 plus 1 is negative 3. Negative 9 plus 1 is negative 8. Negative 16 plus 1 is negative 15. Negative 25 plus 1 is negative 24. Now we can see that all my x's are actually negative, and they're getting more negative for increasing y. So that tells me that we've actually properly pulled off, because my original function would be like this. This function is going to be stretched and reflected in the y-axis. So it's going to show up here. And that's what the table of values gave to us. And that's all we really need to do for radical transformations. The same exact thing we were doing for function transformations. But let's do one more example, just to drive it home.
Virgil Boomer, you have a message at the office. Virgil?
So let's say I had a function transformation of the type y is equal to negative square root of 1/2 x plus 1 minus 2. Okay, if there was no number here, if it was just 1/2 x, I just assume that h is 0. It's not 1. When there's nothing for a and b, we assume 1. But for h and k, if it's 0, we assume 0. But in this case, I'll work with an h of 1 minus 2. That is some ugly stuff there. So, negative square root of 1/2.
Ksenia Brinson to the office, please. Ksenia?
So, I look there. I'm going to identify what all my letters are. That's the first thing I'm going to do. I have a negative, invisible 1. So a is negative 1. I can already tell I'm going to be reflecting in my x-axis. My k is 2. So for all my y coordinates, I'm going to be multiplying by negative 1, adding 2. And then b is 1/2, which means that I'm going to be 1 divided by 1/2 is 2. I'm going to be multiplying all my x's by 2. And my h is negative 1, so it's a positive 1. And then I can create my new table of values and just get her done. So, negative 1 times y plus 2. Negative, so I'm doing my y's. Negative 1 plus 2 is 1. Negative 2 plus 1 is negative 1. Negative 3 plus 1 is negative 2. Negative 3, negative 4. Oh, this does not look great. I done made a mistake. Negative 1 plus 2 is 1. Negative 2 plus 2 is 0. There we go. Negative 3 plus 2 is negative 1, negative 2, negative 3. There we go. There's my new y's. And then my x's I'm going to multiply by 2, add 1. 1 times 2 plus 1 is 3. 4 times 2 plus 1 is 9. 9 times 2 plus 1 is 19. 16 times 2, 32 plus 1 is 33. And 25 times 2 plus 1 is 51. Holy crap. So we have just stretched my function horizontally.
Wells to the office and Carson Howard.
And we have reflected it as well in my y-axis, or in my x-axis, so that my new function, my original function, will look like this. And my transformed function, at x is equal to 3, we have y is 1. Oh, so that was my original function, it started there, and my new function will look like this. Something like that. It's going to be reflected and really stretched horizontally. But I'm not a graphing genius. For graphing, you have a nice website where you can actually check your work by just writing in, but Desmos.com. Okay? This is radical function transformations. You should probably watch my video on function transformations because that's what this is based off of. But I'm going to go eat something. Bye!